is Professor Masaki Kashiwara from Kyoto University, and he's going to talk on quantization of contact manifolds.
Okay, thank you very much. And I'm very happy to speak. I'm very happy to speak here at the IMPA, and I'm very surprised with the good atmosphere here and the good climate and good. Anything is planned. Okay, so today I want to speak about the quantization of contact manifold or symplectic manifolds. And the starting point is the theory of linear differential equations. And that is on the base manifold, on some manifold we study over there. But the quantization means that we work as a cotangent bundle on that bundle to analyze the differential equations. And that is a starting point. So let me explain first the differential equations, or more specifically, it is a linear differential equations. So those parts are studied in the
right, bigger.
I'm sorry. Yeah, in 50s. And now I think it is very well understood. And now the focus is to the nonlinear differential equations. But I think it gives some other aspects now with a connection with other fields like the representation theory or mathematical physics. But it is again in another context that it is a good framework to give something to those things. So let us start some complex manifold. And we consider so-called sheaf of differential operators on X. So that is written with the coordinate system, alpha over X, where alpha is a multi-index, say it is n-dimensional, that is called n-tuple of non-negative integers, and the differentials, and the x, alpha 1, and the x, and alpha n. And that is a finite sum. And so we understand the linear differential equation as D module M. So that is our main subject, object, and we understand it as a linear differential equation. So that is in the following way. So locally, perhaps that have some presentation that is a quotient of some D modules, some free modules, and with some finite many variations. Then, if you consider home, the D linear map from M to OX, for example, OX is a sheaf of harmonic functions, then it is easy to see that that is the one from here, so U in O and 0, such that P, the matrix of differential operators, kills U. So it means to consider this object is nothing but to consider the equation P equals M. So that is a starting point. And of course, here we can replace OX to other things. So the point is, of course, dx, the differential operators, act on the sheaf of harmonic functions. But we can replace here with other D modules, such as G-infinity functions and so on. But I think we are not going there. But I want to see micro-localization. of this situation. So that is, we are considering on X the base manifold, but now we want to consider them on the cotangent bundle. So that is a cotangent bundle. So if X has dimension n, then the cotangent bundle has dimension 2n. And as you know, it carries so-called a simplex structure. So that is a very particular variety. And we want to localize D to some object on T star X, the cotangent bundle. So with some coordinate system, so we consider this differential operator, say P, as a linear combination. We group the homogeneous part, say X, J, where Pj is just the homogeneous part with respect to the derivative. Of course, it depends heavily on the coordinate system, so that's the derivative. It depends heavily on the coordinate system. So to give a differential operator is nothing but to give a function, say x and c, and that is c, pj is polynomial in c and homogeneous with respect to c and degree j. So to give such a differential operator is equivalent to giving such series of homogeneous polynomials in C. So we shall generalize this situation so that we admit not only the polynomial in C, but we admit other any functions. So take omega, say, an open set in X, and we define EXM over omega. So that is a sheaf on T star X that assigned to omega the series of Pj. J is less than m, and J may be negative, and Pj is holomorphic on omega and homogeneous with respect to C and of degree J. So J plus some growth condition that I will give here because there's no time, growth condition. So this is the sheaf on omega, and we just consider EX, EXM. And in fact, this is doesn't so proportion is first. So the definition is the definition uses the coordinate system, but in fact it does not. It is well defined. It does not depend on the coordinate system. And secondly, if we define PQ, we can define the product of two things. That is, first, it's not very important. So more or less, the product of Q, like the Leibniz rule for differential operators, then that is a well-defined product so that Ex is a mean, is a sheaf of mean. So it means it gives canonically a ring structure on Ex that is independent from the coordinate system. So it's a kind of localization. So for example, in algebraic geometry, that is you consider polynomials and you can consider functions on Cn. And here we use this technique. And the third one is if you M goes to, say, sigma M. So we take the principal part, the Pm, Pm. So this is a homogeneous function of degree M with respect to C. And I write by O T star Xm, the sheaf of harmonic functions homogeneous with respect to C of degree J, of degree M. So if we like, so it is well defined. So it does not depend on the coordinate system. And moreover, if P satisfies that if its principal symbol is invertible, then P itself is invertible. So it is like the the localization. It resembles to the localization. So the principal symbol or the value of the principal symbol has a role, plays a role of the function. You take the value, then if the value of a function doesn't vanish, then it is invertible, so that is the corresponding statement. Okay, so another statement is, of course, it is well known, but so it connects the symplectic structure on T star X and the sheaf of ring Ex. So on T star X, you have a canonical one form, say omega. So with the coordinate system, so that's the canonical one form, and the omega gives a symplectic form, dxi. And so they are symplectic. So it is a symplectic manifold. So you can define the Poisson bracket for two functions on T star X. So I won't give the definition, but that is given by, in this way, using coordinate system minus exchange. So that is a Poisson bracket. And this is defined only by the symplectic structure on T star X. And the relation of this sheaf Ex and the symplectic structure of T star X is as follows. First one is if you take P in EM or P nu, 1, 2, then P1, P2, the product is order M1 plus M2, and the principal symbol is the product of the principal symbol. That is very natural. And the other is, if you consider the commutator, P1, P2, the commutator. So that is P1, P2 minus P1, P2. So that is E of M1 plus M. It is of order M1 plus M2 minus 1. And the principal symbol of the commutator is the Poisson bracket of the commutator, of the principal symbol. So that is the relation of this ring EX and the symplectic structure of this X. So more or less, so that is so the sheaf of ring EX is not commutative, and the gap or the non-commutativity is described by the symplectic structure. Okay. So another important theorem is if M is coherent. So that is some finite condition that I will not explain here, but module. Then its support of M, the set of the points where M doesn't vanish, is, of course, it is a complex analytic manifold, submanifold in Syst X, but it is so-called involutive manifold. Involutive means if, say, two functions vanish on the support M, then their Poisson bracket vanishes. So that is one of the fundamental notions in the symplectic geometry. And in particular, if X has the dimension n, then the dimension of T star X is 2n. And in fact, involutive manifold, it implies that the dimension of the characteristic variety or support of M is larger than n dimension. It cannot be so small. It has at most 1/2 of the dimension of the T star X. Okay, so there is another theorem that says the following. So now you take two manifolds with the same dimension. And you consider their cotangent bundle. And assume that you have some open set and some open set of the cotangent bundle. And you have an isomorphism that is symplectic. So say phi. So phi, in fact, we assume more. It is homogeneous with respect to C. So phi is symplectic. It means it preserves the two form, d omega, and it's homogeneous. Homogeneous means there's a C star action on T star X, fiber-wise, and Y also, and this map commits with that C star action. And this condition is, in fact, equivalent to say that it preserves the canonical one. Okay, we assume this. And the problem is, of course, that is more, so if there is an isomorphism between x and y, then it induces such simplex transform. But of course, all the simplex transform does not come from such correspondence of the manifolds. Those simplex manifolds are much more richer, richer than the isomorphism of base manifold. So assume that such phi is given, and then locally on omega x or omega y, there exists an isomorphism between those two rings. And that is more or less, it is not unique, unfortunately. So there are a lot of choice because EX has many automorphisms. Because EX is not commutative, so if you take an invertible element and you consider the adjoint action, then that gives an automorphism of EX. So it cannot be unique. But it is more or less unique up to such adjoint or such adjoint automorphisms. And the non-uniqueness is a kind of property that we cannot get rid of. Okay, so quantization. So now we consider the symplectic manifold, or more precisely, a manifold to n, say, to n-dimensional manifold with theta x, with omega. It corresponds to this one form, and such that d omega gives the symplectic form on x. So d omega is symplectic. And we assume that further that omega does not vanish everywhere. Right. So it's a classical result that x is locally isomorphic to theta x. So it means you can cover this by an open set, and each cover is embedded or is isomorphic to an open set in the cotangent bundle for some xi. So you can define UI, say, it is, you have EXI on theta xi, and that is embedded in theta xi, so you consider its restriction. So that gives a sheaf on UI on each cover, and by this theorem, so EUI, say, at the intersection EUI and EUJ are locally isomorphic. So, but in fact, in general, so there is no sheaf of ring on X. So there is no, in general, there is no sheaf on, say, EX, such that locally isomorphic to EDR. We cannot expect that such a sheaf of ring exists. We need some obstruction theory to give such a things. Yeah, but by the way, I think in a real case, X is real, then I think concept result says it exists, I think. But in general, not. So, but even if such ring does not exist, there is a stack. So there is a stack, canonical stack on X. So what is a stack? A stack is more or less a sheaf of categories. So to any open set, you assign some category. And for two open sets, including one, including together, then there's a restriction function. So it's something like the sheaf of categories. And there is a stack, say, mod X, such that, so mod X is locally isomorphic to mod E UI. So it means you cannot patch those sheaves EUI together. It's impossible in general. You need some obstruction. But the category of modules can be patched together. And that is canonical. Canonical means if you have two symplectic manifolds and if you have symplectic transforms, then you can define canonical transforms. So that is canonical. So that is a kind of algebraic part of the theory. So it means we consider D, and we consider E, and so on. But those are described in algebraic terms. I mean, it is functions on them. But there is some topological counterpart of this. So perhaps to go there, I will explain so-called regular holonomic modules. So I said that if you take M, EX module, or coherent EX module, then its support is invariant. And so if it is Lagrangian, Lagrangian means the dimension of the invertible manifold is at least dimension X. But if the dimension attains the minimal one, dimension of X, then we call that is Lagrangian. So in this case, we say that M is holonomic. And if there is sub-module, sub-E0 module, E0 is a subchief of EX, and this is a ring, subring. This is a ring. And E is a kind of localization of E of them. There is such one, such that, then M0 bar, say, M0 over, yeah, it contains E minus 1 as a ideal. So you consider the quotient. So this is a O0 is E0, E minus 1 module. So that is always true. So the condition is if there is such an M0 and M0 bar is annihilated by I, where I is all the function homogeneous of degree 0, such that F is 0 on the support plane. So because the support of M0 bar is exactly the support of M, so if you take a high power, then it kills. But the condition says we can find M0 such that I itself kills M0. So D module M is called regular holonomic. Yeah, but I didn't say the conclusion. So if it satisfies this if condition, we say that M is regular holonomic. So D module is regular holonomic, means just you consider EX and you EX contains DX, so you can say D, or more precisely pi inverse is holonomic, a regular holonomic. And the theorem says the following. So you consider regular holonomic, the category of regular holonomic modules. So this has a very special property. It is an abelian category, and locally, or it depends on the scheme, but any module have finite length. So that is a very particular category. And this one is equivalent, so-called the category of perversives. I will not go to the definition of perversives, but so I'll tell only the correspondence. So to M, a regular holonomic DX module, you associate, it's in a quantum variant form, but we can do variant form also, covariant form also, DXM OX. So you take home, in fact, in the derived category, and so it is a complex of sheaves of sheaf vector space. And we consider them in the category of, in the derived category of complexes of shapes of sheaf vector spaces. And that has some very particular property, and that is called purpose shapes. And that gives a one-to-one correspondence between two categories. And this category, the category of purpose shapes is very topological. So it only depends on X topologically and a little bit with a complex structure also, but it is very topological. And for regular holonomic D modules, you can extend it to regular holonomic E modules. So you have, so now we come back to the situation of a symplectic manifold. And then you have this stack that is locally isomorphic to the modules over E. And inside, you can define, of course, regular holonomics. Those notions only depend on that one. So it is very easy to see that we can define regular holonomic ones as a full subcategory. So I think still now it's not known, it's conjectural. So the conjecture is there exists some topologically defined category or stack. So say I say micro-locally or quantized purpose. So recently in Vassiliev did it to define those things when X is a potential bundle. And I think he is now almost established, but it's not written yet, but this conjecture, the existence of such things. Okay. So this category have some very particular property. So if you take, say, M regular holonomic, so by the definition, the support is Lagrangian. So the half dimension of the total space. So support of M, say 2n is the dimension of the symplectic manifold. Then support of M has dimension n. And so there are particular property, I mean, so take a submanifold in X. Or the analytic subspace, complex analytic subspace in X. And so if dimension of Z is smaller than n minus 1, so this has the dimension n, but smaller than, and you take two regular holonomic ones. Then, if you, let me see, M, what about today? So, and consider homomorphism, the morphism between them, homomorphism between them. And if it is 0 outside Z, then you equal Z. So it means the morphism is determined uniquely outside n-1 dimension. And the second is assume that it is at most n-2 now. And you have similarly m and n, regular holonomic one, and assume that outside Z you have a morphism. Then you extend. To X. But of course, the extension is unique by the first property. So it's very similar to the, say, harmonic functions. Say the harmonic function is 0 outside n-1 dimension of variety, then of course it vanishes. And if it is defined on outside n-2 dimension 1, then it extends. So that is the most common phenomena that we can see in the theory of harmonic functions. And so now conjecture is, so assume now that, yeah, first you can now expect what I'm going to say, but is less than n-3, and m is regular holonomic 1, it is given outside Z. Then m is extended to whole X. So, of course, by those 1 and 2, if the extension exists, it is unique. But the conjecture says it is, in fact, it extends. So basically, what it says. So I think, I'm now studying that, and I'm going to near the end, but I think it is not. I'm not quite sure that that's. So I want to say that. So this property means to give this category. So for it is in plus outside the. So when V is, say, smooth Lagrangian, so and consider regular holonomic and support of M is contained in V. So it is more or less equivalent to the category of local systems. Local systems only. So it means on the non-singular part of the Lagrangian, the structure is very well known. And the first property says, so you have to give another structure, an extra structure on codimension 1. And on codimension 2, you need some condition of the extendability. And that's enough to give that category. I think, just to end my talk, I want to say something about that. So you can think why those categories are important. I think so. Nowadays in mathematical physics, they are so. For example, in the mirror symmetry. For example, you consider complex manifold, and in the counterpart, they consider symplectic manifolds. And there is some equivalence among them. It means that you can associate something to those manifolds. One for complex manifold, the other symplectic manifold, and those two are the same. And so those one, I think it's not exactly the same, and you need more modification and so on. But it gives something to associate something, to associate to the symplectic manifold. And that has a very interesting properties. And yeah, so that is why I'm now interested with those conjectures. Okay, so thank you very much.
Okay, thank you for your talk. Questions? Oh, yes.
Yes.
Is there any formulation of anything like mirror symmetry in this framework?
I don't know. For that, I don't know. Yeah, I don't know. It's,
So
yeah.
in other words, I mean, is the counting of holomorphic curves or anything like this appearing naturally
yeah.
in the context of deep
Yeah. No, I understand what you say, but I don't know. Perhaps it is something like that. It can be. So in some very special manifolds, they coincide, but in general, it's not. So I think it's not like the Fukaya category or those kind of things. It's very, very different. It's not global.
And my second question is there anything like a generalization of the Mukai transformation in this context which would fit with anything like mirror symmetry?
I don't know. Perhaps, let me see. Yeah, there are, but there is not, because, yeah, there are, for example, but I think for that we need more structure than regular holonomic D module or regular holonomic E modules. We have to consider micro-local mixed Hoji modules or such richer structure with. And so, for example, there are some works that say that some how to say, some derived category of coherent modules of one and the other are equivalent, such as Mukai's work. And I think one a part of them can be explained like that. I mean, there is equivalence in that category as with Hoji modules. Then if you go to the O module, by taking the graduation or the Hoji filtration, then you can get such equivalence. So it's not, there is some connection, but I think the connection is it's like that. I mean, not very big. A part is, there is some connections. That I think. Does it answer your question?
Maybe just the last one.
Yes.
Is there anything like deformation, I mean, an analog of deformation of quantum cohomology? It is in the same way as quantum cohomology deforms the cohomology ring. Do you have anything like this?
I don't know. Yeah, I want to know about that. Yeah, that is a good question. I think that is a good question. I mean, so I think the best way is to associate some category and you take the home, then you can get quantum cohomology ring. But I don't know that.
Okay, any more questions? Okay, so let's thank the speaker again. And we break for lunch now.